our trapezoid rule said that we could take a function and we could approximate the area under that function using these trapezoids, and the formula that we came up with was 1/2 times delta x times the quantity f of x0 plus 2 f of x1 plus 2 f of x2 plus dot 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 all the way up to 2 f of x n minus 1 plus f of xn. And so we had this whole sum going on here, and the funny thing about this formula was that we ended up with 2 of every single term except for the first one and the last one when we only had 1 of those. And so this formula is kind of weird. We went through how to come up with this formula, and hopefully over the break you were telling your dog or your cat or your neighbor or maybe one of your friends about this trapezoid rule, and so you feel really comfortable with where this formula came from. And if you don't, then you might want to spend some time this week reminding yourself where this formula comes from and how to explain it to somebody else in this class. Maybe imagine explaining it to somebody who missed class on that day. All right, so be able to carefully explain where this formula comes from.
So on the test, you want us to do the steps to get to that formula.
That's right. That's right. So be able to explain and be able to draw the picture, and then the picture of the trapezoids under the curve. Be able to say what is the formula for the area of a trapezoid, and then write out the expression with all the areas of the trapezoids and simplify algebraically until you get to this. Okay, are there any questions, other questions about this formula that's up here? Okay, well, I left you with 2 questions to ponder over the break, and those questions were, number 1 is, how do we know how good our approximation is? And the second question is, if we have a required tolerance or allowable error, how do we decide how many trapezoids to use? In other words, how do we choose n? And these were the 2 questions that I left you with, and we want to answer these questions during our first hour of class today. All right, so the example that we were looking at last time, we were trying to approximate the integral from 1 to 2 of 1 over x cubed dx. And we did this using T4. And so what do I mean by using T4? I mean that we're going to use the trapezoid rule, that's what T says, and I'm going to use 4 subintervals. So T means our trapezoid rule, and n is going to be equal to 4. Okay, so we did this and we came up with our T4 value of 0.389, or something very, very close to that. And I also said that you should check by hand that the exact value of the integral from 1 to 2 of 1 over x cubed dx is exactly equal to 0.375. And this one is one that we could do by hand. Now, in general, we're not going to be able to compare our approximation to an exact value because the whole point of doing the approximations is that we cannot find the exact value. So in this example we can compare, but usually you can't. All right, so we had this, and so we could calculate our error exactly. And so our error was the difference between the exact value, the integral from 1 to 2 of x cubed dx, the difference between that and our t4 value. And so we could do that calculation, and we have 0.375 minus the value for t4, which is 0.389, and take the absolute value of that, and we come up with 0.014. And so this was our actual and true error. All right, are there any questions about finding that exact error? This is how far off we were by using 4 subintervals, using the trapezoid rule, rather than actually calculating the integral itself. Okay, so we want to continue with this, and I want to answer these questions over here. And so the next question that we want to ask is, how good is our approximation of the integral from 1 to 2 of 1 over x cubed dx if we use the trapezoidal rule with n equal to 10 subintervals. All right, so this is the next question I want to ask. Now, there's a couple of ways I can go about trying to answer this question. Number one, I know what the exact value of the integral is. I could then use my formula over here for coming up with t10, and then I could say, all right, I'm going to take my exact value minus t10, and I could subtract them and figure out what my actual error is. But that doesn't really help us with question number one when we don't have an exact value for our integral. All right, so we need a little bit of help here. And the help that we get comes from a formula and an expression that we're not going to talk about where this formula comes from. Where this formula comes from is something that you'll learn about if you take numerical analysis in your senior year. If you're an applied math person, you're going to learn all about this formula. We're just going to use it. Okay? So we're going to take it for granted, maybe talk vaguely about why it kind of makes sense that it's the right formula, but basically we want to learn how to use it. Okay, so here's our formula. This is our error estimation for the trapezoidal rule where Tn is approximating the integral from a to b of f of x dx. So here it is. Suppose k is an upper bound for the values of the absolute value of f double prime of x on the closed interval from a to b. Then the error from our trapezoidal rule is less than or equal to k times b minus a to the third over 12n squared. Alright, so this is totally out of the blue, right? I just like, poof, lightning bolt, here's this crazy formula I've just written up on the board. And here's what it said, and by the way, this error here, your book might write it as E subscript T, because they talk about error for the trapezoid rule, error for the midpoint rule, error for the right-hand rule, left-hand rule, and as well as Simpson's rule, which I mentioned last time is instead of using straight lines to approximate, we're using parabolas to approximate the curve. Alright, so looking at this expression, this says if I know something about the second derivative of this function up here, then I can tell you, and the other pieces of information here, we've got the number of subintervals, that's our n, and we have our b and our a, those are our boundaries on our integral. If I know this information, and I know something about the second derivative of my function, then I can tell you that the error by using the trapezoid rule is no worse than this expression right here. So this is like a ceiling or a cap on the error that we get when we use the trapezoid rule.
Weren't we using approximate integration because we couldn't do the first derivative very well?
Good question. We're using approximate integration because we can't find an antiderivative.
I mean the antiderivative.
Yes, so the idea here is that it's easy to find derivatives. Now when you're in Calc 1 it doesn't feel like it's easy, but we can find derivatives for a lot more functions than we can find antiderivatives for.
I meant antiderivative.
Yeah, so the challenge here is that here it's hard to find an antiderivative, but it's going to be okay for us to find a first derivative or a second derivative. We just can't go backwards.
Oh.
Yeah, so that's the difference. We can take derivatives, we just can't take antiderivatives.
Yeah.
Difference.
Okay, other questions or comments about this? For those of you who might be wondering where this formula comes from, here's sort of the idea about this k value. When we talk about a second derivative, what does the second derivative tell us about a function?
The inflection points.
It talks about inflection points, and so those are specific points, and it also talks about the concavity of the function. So whether a function is concave up or concave down. Inflection points happen when our second derivative is equal to 0. Now, when the second derivative is very large in a positive direction, that tells us that our function is strongly concave. So large f double prime means that my function is very, very strongly concave up, as opposed to a small f double prime. I don't have quite so much concavity going on. And so when I'm talking about a trapezoid rule, and if I connect 2 points with a straight line where the function is very concave, then I'm going to have a much larger error with my straight line approximation than if I connect a straight line between 2 points where the curve is not very curvy at all, not very concave at all. And so that's where this idea of the maximum concavity has to do with the ceiling on our trapezoid rule. So this is just a thought bubble off to the side. You do not, if that did not make sense to you, that is not a required piece of the course. That's just sort of a thought idea on where that maximum comes from.
So K then is just a maximum?
K is a maximum.
Okay.
That's
and
right.
then to find that, would you have to take a F triple prime set of equal to 0 and then...
So that's a really good question. The answer to that is yes with an asterisk. Because we need to find the maximum F double prime, which means figuring out where F double prime has local maxes or local minimums, and then, so setting F triple prime equal to 0 and solving for those. We're not going to go through all that work, we're going to do this graphically. Okay. But that is ideally what you would want to do if you're going to do all the dirty details. Okay, so let's take a look at an example here. So our question here is, how good is our approximation of the integral from 1 to 2 of 1 over x cubed dx if we use the trapezoid rule with n equal to 10 subintervals? So we are going to, another way to write that, another way to say that example is to, so we will estimate the error of using T10 to approximate the integral from 1 to 2 of 1 over x cubed dx. Okay, so we're going to estimate the error, and what we're going to say is the error is going to be no bigger than whatever number we get out on this right-hand side. So we need to figure out what this number on the right-hand side should be. So our error, the error from our trapezoid rule, is less than or equal to k times b minus a cubed over 12n squared. And so we want to fill in all the information on the right-hand side, and then we'll know that our error is no bigger than this number on the right side. So some easy things to fill in. First of all, I see my subscript of 10 here, and so that's my n, and so I know that n is equal to 10, number of subintervals. And I can look up here, and my b and my a, those are my upper and my lower bounds, so b is equal to 2, and a is equal to 1. And so I've taken care of the n, the b, and the a. And the hardest part about this formula is figuring out what that k value is going to be. And so k is the maximum value of the absolute value of f double prime of x on the interval from a to b, the interval from 1 to 2. And Matt was totally right. This is an example of one of those absolute max-min problems that you talked about in Calc 1, where you have to take the derivative of this function in here, set that derivative equal to 0, solve for all your critical numbers, and check the height of the function both at the critical numbers as well as at the endpoints. But we're going to simplify that a little bit. Instead, what we're going to do is we're going to graph y equals the absolute value of f double prime of x on the interval from 1 to 2. So I have to start out by looking at what my original function is. My original function is f of x is equal to 1 over x cubed. And I need to find my second derivative. So before crunching any derivatives, I'm probably going to want to rewrite my function, x to the negative 3. And then taking a derivative, not antiderivative, but derivative, I have negative 3x to the negative 4. And then my second derivative, f double prime of x, is going to be 12x to the negative 5. Okay, so if you have your calculator, please pull it out. And please graph 12x to the negative 5, where your x values go from 1 to 2. So make sure your window, your x values are going from 1 to 2. And then compare your pictures. Alright, does anybody have a picture that looks just like your neighbor's picture? Riley, what does your picture look like? If you were to kind of draw it out in the air.
It just kind of goes down.
Okay, so something like that?
Looks good.
Alright, okay, great. And we only care about this thing between x equals 1 and x equals 2. Now, note here that there's a little bit of a difference here. Our k value is the maximum value, the absolute value of this function. And so in this particular case, our second derivative, f double prime, is always positive. If that guy had dipped below the x-axis, then we would probably want to graph the absolute value of this. And so technically, I want absolute value bars around my function. And so on this interval from 1 to 2, as I'm looking at this function, I can see from the picture that the highest point here occurs at x equals 1. And so my maximum of the absolute value of f double prime of x occurs at x is equal to 1. Now, when x is equal to 1, what is the y value of this function?
12.
It's 12. And if I wasn't sure about that, I could either do a trace on my calculator, or I could plug in x equals 1 into my function, and I get 12 times x to the negative 5th. So I end up with a value of 12. So the maximum value, so the maximum of the absolute value of f double prime of x occurs at x equals 1, and that value is 12, which tells us that k must be equal to 12.
So I put it in my calculator as a fraction when I did the trace and I got a decimal,
Okay.
and I'm not entirely sure why.
So
The
did
Y
you,
value.
when you did your trace, once you actually type, if you type in an x value of 1, what do you end up with?
0.08.
0.083 for your y value.
Yeah.
That doesn't sound quite right.
I just put 1 over 12 to the x raised to the
I think that might be your problem, because so what you've written, I think, is 1 over 12 x to the 5th.
Yeah, is that not right?
Not right. So you want this 12.
The numerator front?
You can either put the 12 in the top, or you can put it out front, but not in the denominator.
Cool.
Good. Okay, other questions about this k value? So again, in this particular example, our second derivative was always positive, so the absolute value bars did nothing for us. If this guy had been a negative, if it had been upside down, then we would have thrown in the absolute value bars and flipped it back up. So it's the largest y value once everything is made positive. Okay, so now we have our k. So we've got our a, our b, our n, and our k. And so this tells us that our error for our trapezoid rule is less than or equal to k, which is 12, times b, which is 2, minus a, which is 1, cubed, over 12 times n, which is 10 squared.
So we went from 1.4% with 4 to just 1% deviation with 10.
Okay, so what did you come up with as once you crunched these numbers?
It's just 1/100th because the 12s go away.
Yeah, so these guys cancel, and we're left with a trapezoidal error of less than or equal to 0.01. Okay, so this says that we are within 0.01 square units of the actual area under this function by using 10 subintervals. Now, in terms of percentage error, then you want to take that value divided by the actual area, which in this case we know, but in general we won't know. So we can know how far away we are, not as a percentage, but as an actual value. All right, so that's our final answer here. If we use 10 subintervals, we will be within 1/100th of the actual error. Are there any questions about that? Okay. So there's a little bit of hand waving with this 12 right here. If we had come up with something that maybe our interval only went from 1.5 up to 2, and we came up with a decimal number here. Technically, this number here and this k up here is just an upper bound. And so you could actually say, oh, well, I see that this is 12, but I'm going to use a k value of 12.5 or 15 or anything, as long as our k is a number that is greater than or equal to the maximum of our second derivative, then it's going to put a ceiling on our error. So we know right now that we're within 1/100th of the actual answer. If you have a poor approximation for k, you're knowing that you're going to be within a less how do I want to say that? If we chose something like 15 up here, that would make this number larger, and then we'd say, well, our error using 10 subintervals is going to be within, I don't know, maybe 2/100ths. So our approximation wouldn't know it to be as good. But so we want to pick a k value that is as close as possible to the largest f double prime that we can find. We never want to underestimate that, though. Whatever number we choose for k must be greater than or equal to any f double prime value within the interval. Okay.
But I mean, we could always just use, like how we did with the formula, we know that the maximum's at 1, so we just plug that into the formula.
That's right. That's right. So the things that could be kind of funky is if when you plug in 1, if you get something out that's like 12 point some long decimal, what you don't want to do is round down. Always round up. Okay. Other questions?
So is that formula right there, the K, do you want to say to, yeah, that one? Is that something that we just need to memorize?
So that's a good question. The answer to that is, this formula is coming totally out of the blue, so I will give you this formula on the test so that you don't have to have it totally memorized in your brain. However, you will need to know what each of these letters mean in the formula. So I'm not going to remind you that k is the maximum of the second derivative, but I'll give you this formula on the test. But you have to know how to use it.
So that 12 is always going to stay 12.
That's right. That's right. This formula right here is fixed and will always be 12. That's always squared, and that's always cubed. Other question? Okay. So let's wrap up with one final example here. And this question addresses the second problem that we were left with before the break, and that is, if we know we have a tolerance that we need to achieve, how do we know how many subintervals we need? So here's our next question. How large must we choose n so that our Tn approximation is within 0.0001 of the actual value of the integral from 1 to 2 of 1 over x cubed dx. So this is the question of, all right, we want to approximate this integral right here, and we need to be within 1/10,000th of the actual value of this integral. How many subintervals do we need? So we need to figure out an n value. Now, certainly, since here, with 10 subintervals, we were within 1/100th of the correct answer, we're going to need more than 10 subintervals. All right, so our formula says that the error for the trapezoid rule is less than or equal to k times b minus a to the third over 12n squared. Now, I'm going to put an asterisk on this because at first glance, what I'm about to tell you is going to sound very counterintuitive. My guess is that what you may be thinking right now is, oh, I can put in 0.0001 here on the left side, I can put in my b and my a and my n, and then I can solve for k. Or, no, I'm sorry, I can put in my b, my a, and my k, and then solve for n, and that would be great. It doesn't quite work like that. Because think about if we put this 0.0001 over on the left side, we're saying that the error is less than or equal to, the error is smaller than this number over here. What we need to do, we need to force this error to be smaller than this number. And the only way we can do that is if we put a ceiling on this expression right here. So what we need to do is we need this expression, which is keeping our error small, we need for this expression to be smaller than this number. We need to force k times b minus a to the third over 12n squared to be less than or equal to 0.0001. So it looks like my inequality is backwards. But really what I'm doing is saying, here's my error that I'm trying to force to be 0.0001. I've got a cap on that. That's this formula here. I've got to make sure that that cap pushes down on my error so that that cap remains smaller than my tolerance that I'm requiring. Okay? So my inequality looks backwards, but take that home and think about it and convince yourself that we really do want to make this cap smaller than our tolerance. And so, okay, so this is our expression. We can fill in some information. We're trying to solve for n. And so things that I can fill in right away, I can fill in my b value, which is 2, and my a value, which is 1. And if I was starting from scratch, I'd have to go back and I'd have to find my f double prime, graph it, and figure out my k value. And so in this case, k is equal to 12, which is our same as our other example, because it's the same function, same f of x, same boundaries, everything is the same, so our k value is the same. Otherwise, we'd have to redo that whole example, find the second derivative, graph it, all that kind of stuff. And so what we have here is 12 times 2 minus 1 to the third over 12 times n squared is less than or equal to 0.0001. All right, are there any questions about setting that up? All right, so now I've got this inequality. I'm trying to solve for n. So the first thing I can do is, in this case, I can cancel these 12s. And I have on this left side 1 over n squared is less than or equal to 0.0001. My goal is to solve for n, so I can multiply both sides by n squared. So I have 1 is less than or equal to 0.0001 n squared. Now, before I go any further, comment on algebra here. When I'm working with inequalities and I'm multiplying, what do I have to be careful about?
Negative number.
Yeah, I have to worry about multiplying by a negative number. Now, in this case, n squared, I know that n is, first of all, it's squared, so automatically positive. But even so, I know that n is a number of subintervals, so that's automatically a positive number. So I don't have to worry about my inequality here. I can divide both sides by 0.0001. Also a positive number, so I don't have to worry about changing my inequality. And so I end up with 10,000 is less than or equal to n squared. And now I can solve this, since I know everything here is positive, it's legitimate to talk about square roots. And so I've got an n on the right side, and square root of 10,000 is 100. So this tells me that I need at least 100 subintervals in order to get within 1/10,000th of my actual value. We need at least 100 subintervals to approximate the integral from 1 to 2 of 1 over x cubed dx to within 0.0001 of the actual value. End of story. All right, are there any questions about solving this? So we've just answered 2 questions.
So for just, to solve for the n, we just flip them around and put in the other.
That's right. So what we're doing is we're looking at this and saying we're going to put over here our goal tolerance. And so our goal tolerance is bigger than this number, and this number is going to be bigger than our actual error. So we flip those around, or we put our goal tolerance over here on the right side, and we solve for n. The easy things to fill in are the a and the d. The hard thing to fill in is the k, because you've got to figure out f double prime, graph it, find that maximum value of f double prime. All right, other questions or comments? All right, so we will let the trapezoid rule rest here. And please take turns about this particular section. Oh, you're in Calc 2, you can learn about the sequences and series stuff. And what I found about this section is this is a completely new and different animal from what you have been studying in calculus so far. And so some of you may come away from this section saying, that stuff is totally awesome. And I absolutely love it. And some of you may come away from this section going, all right, well, I can work with these things and I can handle them and I can talk about these sequences and series, but maybe I don't love them so much. And that's okay. But what I want to talk about today to start out is I want to give you a little bit of an overview of what these sequences and series are really about, what the end goal is for Chapter 8. And the end goal, if I look at something like the function y equals e to the x. Now, if I draw a picture of this function, I know immediately what this function looks like. It's a function that looks something like this. It does not cross the x-axis. It crosses the y-axis at y is equal to 1. And what I'd like to do is compare this function to a couple of other functions. And I want to compare y equals e to the x to y is equal to 1. That's going to be my first example. The next function I want to compare y equals e to the x to is y is equal to 1 plus x. The third function I want to look at is y is equal to 1 plus x plus x squared over 2. All right, so these are things that you can do on your calculator. You can graph y equals e to the x, and you can graph y equals 1. Y equals 1 is a horizontal line that goes directly through y equals 1. So you can do that on your calculator. I'm going to show you a picture on Mathematica. So what you see here is you see y equals 1, y equals 1 plus x, y equals 1 plus x squared over 2. And then I have a whole bunch of others where I've added on one term each time. Okay? So I'm looking at a list of functions here. And each function is a polynomial. And each function is adding on one more term from the previous function. Okay? So the next one on the list down here is going to be y is equal to 1 plus x squared over 2. And if you can read, this is kind of small. This is x cubed over 6, which there's a pattern going on here. This is x to the third over 2 times 3. I'm looking at these, and these are all polynomials, and each one is adding one more term onto the previous one. Now I scroll down here a little ways, and I have a picture. And the picture that I have here is I have this blue curve, which is e to the x. And right now, what I've drawn here is y is equal to 1. Now, if I hit the plus sign, so right now, see I've got a 0 up there. That means I'm looking at the degree 0 polynomial. The next polynomial is adding on a degree 1 x. And so if I hit the plus sign, then I get the function y is equal to 1 plus x. My next one, if I hit the plus sign again, I'm going to graph 1 plus x squared over 2. I'm going to be looking at a degree 2 polynomial. And if I move another step forward, then I'm going to be looking at a degree 3 polynomial. Now, notice what's happening each time that I add on a term. Okay? My next term, my next one's going to look like y is equal to 1 plus x squared over 2 plus x to the third over 2 times 3 plus x to the fourth over 2 times 3 times 4. So if I add on another term, I've got this new curve. So now I'm going to go ahead and hit the plus sign a few more times, and I'm going to be adding on more and more terms. Now, let me remind you what those look like. Up here we had, this was our x to the fourth over 24. And then we've got all the way up to x to the fifth. And the next time we'll add on that x to the sixth term, etc. And so take a look at what happens as I add more and more terms.
Is this like Newton's recursion, curve fitting, or?
So what exactly is happening here is that each time we add a term onto the polynomial, our polynomial approximation of e to the x gets closer and closer to looking like e to the x. And so if I hit play and watch this curve get closer and closer to looking like e to the x. Okay, the more terms I add on, the closer we get to e to the x. And so the idea here is that we can approximate a function, any fancy function, so I'm going to say a fancy, in quotes, a fancy function using polynomials. The more terms we add, the closer our approximation gets to the fancy function. And so it turns out that, so as you go, notice as I'm adding more and more terms onto this thing, our polynomial approximation is getting closer and closer to y equals e to the x. And so the idea is that if I then allow the number of terms I have to go off to infinity, if I have a sum of polynomials, an infinite sum of polynomials, then it turns out that e to the x is exactly equal to that infinite sum. And so e to the x is equal to 1 plus, and I'm going to write out a little bit more so we can see the pattern here, 1 plus x over 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3 plus x to the fourth over 1 times 2 times 3 times 4 plus x to the 5th over 1 times 2 times 3 times 4 times 5. And if I put a plus dot 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 at the end, that means that sum goes on forever and ever and ever and ever and ever and ever and ever. And so this infinite sum of polynomials is called a Taylor series. And so let's say that I wanted to approximate y equals e to the x, and all I cared about was maybe just approximating right in this little section right here. Well, I could approximate this y equals e to the x using just the first 3 terms of this polynomial here, this infinite polynomial. And so I can use that, and that's easier to deal with than this exponential function. Okay? So I can do that, and so I want to be able to work with that. Now, that's kind of interesting with e to the x, but it turns out we can do this with a bunch of different polynomials. For example, we can write lots of functions as infinite sums of polynomials or we can cut off the infinite sum and use the approximations. So as a second example, another function that we might try to approximate is y equals sine x. And it turns out that we can approximate sine x as x minus x to the 3rd over... Now, these numbers that I wrote out in the denominator over here, 1 times 2 times 3 times 4, that gets really burdensome once you do 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12, etc. So we can shorten that using that factorial notation. And so instead of 1 times 2 times 3 times 4 times 5, I can write that as 5 factorial. All right, so here for sine x, I have x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus, and then that keeps on going and going and going.
How come it's minus?
So why these alternate between pluses and minuses is totally unclear at this point. I'm just telling you what it is. We'll see later on where those pluses and minuses come from.
Okay.
Yeah, totally unclear right now. So take a look at...
Is it because of the symmetry about x with sine?
It does have to do a little bit with that. It also has to, so it has to do with the odd, so one thing here is that sine of x is an odd function, and notice all these powers are odd powers. The alternating part kind of comes out in the wash, and we'll see where that comes from later. Okay, so let me show you this example now. Okay, so here is sine of x. First I've got x, then I have x minus x cubed over 3 factorial. 3 factorial is 1 times 2 times 3. So that's x cubed over 6. And then I've got x minus x cubed over 6 plus x to the 5th over 120. And so look at what happens here. Now here, the number up at the top there is telling me how many terms I've used. So when I have 0, I have, that number's a little misleading. I really have 1 term. So first of all, I'm approximating sine of x with y equals x. And that does a good job right around here around the origin. Or I could chop it off after the next term, and I have x minus x cubed over 3 factorial. And that looks like this. So it looks a lot better right in here, right? And so now what I'm going to do is I'm going to let this play, and we're going to see what happens as we add one more term on at each step of this. So here we go. Let's see what happens. So after you get up to about 10 terms, this polynomial exactly approximates sine of x. So the more terms we add on, the better our polynomial approximation is. So here, let's go a few more. So when I have 3 terms, I've got, oops, I can't just highlight that part. I've got x minus x cubed over 6 plus x to the 5th over 120. And so here I'm using these polynomials to approximate sine x. Now for those of you who like physics a lot, you may be looking at, for small angles, you might have some formulas such as Snell's law when you're talking about lenses and optics and things like that, where you've taken sine of x in a formula and replaced that with just an x. Okay, and so that simplifies your formulas. And so in physics you can do that, and what you're doing is you're taking this polynomial, this infinite polynomial, and chopping it off and saying that sine of x is approximately equal to x, which it kind of is. If you look right in there, yeah, for small values of x, y equals sine x is approximately y equals x. Okay, so these are called Taylor series. These infinite sums which describe these functions are called Taylor series, and that's what we want to eventually get to. We want to be able to write down fancy functions as an infinite sum of polynomials. So in order to talk about that, what we first have to understand, so in order to understand Taylor series, that's what these are examples of. In order to understand these Taylor series, we first need to understand infinite series. So to understand Taylor series, we must learn about infinite series. And before we talk about infinite series, to understand infinite series, we must first learn about infinite sequences. So today what we're going to talk about, or at least we're going to start talking about, is infinite sequences. And that's section 8.1. Section 8.1, the topic is sequences. Is a list of numbers written in a specific order. So I didn't use the word infinite up here. That's understood when we're talking about sequences. We're talking about infinite sequences, which means an infinite list of numbers, a list of numbers that never ever stops. So here's our first example. Our first example is 2, 4, 6, 8, 10, 12, 14, continues on forever and ever and ever. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, etc. Keeps on going. Yeah, so I could keep talking forever and just talk about this sequence for the rest of our lives, but that might be a little bit silly. All right, and so I can give these guys names, and so I might call the first term in my sequence, my list of numbers, I might call that A subscript 1. My second number is going to be A subscript 2. My third number will be A subscript 3. And so then I can keep going, and I've got A4. So each of these, the A is saying, okay, our sequence name is A, and the subscript is the list number in our sequence. And so I might say that A5 is equal to 10, for example. And I can write a generic formula. The nth term, AN, well, I would need to be able to come up with a formula for this. And so if I want to figure out what AN is equal to, I might make myself a table. And so I've got when n is equal to 1, A1 is equal to 2, and when n is equal to 2, A2 is 4, and so when n is equal to 3, my A3 is equal to 6. And so if I just had a generic n, then my nth term, well, I need to figure out a pattern that's going on here. And so when I look at this and say, oh, well, I look at that subscript, and every time I'm multiplying that number by 2 to get the other guy over here, and so AN is going to be 2 times n. And then maybe if I wanted to look at the n plus first term in my sequence, then n plus 1 is equal to 2 times the quantity n plus 1. So it kind of looks like functions, only the difference is that instead of having f of x, the name of my function is a, and the subscript is my input letter. Okay, so similar to functions, and so really I can think of, instead of saying that a sequence is a list of numbers in a specific order, another way to write this is to say a sequence is a function whose domain is the set of integers greater than or equal to some base number. So when I think about this example in this way, what I'm thinking about is when I write down a subscript n is equal to 2n, what this really means is, in terms of, normally we would write a function as, here's the name of our function a, and the input is n, and then our formula that we're going to be using is 2 times that input number. And we're only allowed to use whole number values, 1, 2, 3. I'm not allowed to plug into this function pi. And I'm not allowed to plug into this function 1.5. I can only plug in whole number values. And so I can look at a graph of my sequence, my graph of the sequence AN equals 2 times n. And remember that my input values are only allowed to be whole number values. So I can plug in a 1, and the output that I get is 2. And if I plug in a 2, the output that I get is 4. If I plug in a 3, A3 is 6. And if I plug in a 4, well, A4 is 8. And so this graph of the sequence AN equals 2n is a sequence of dots. Okay, and I am not going to connect the dots because there is no meaning to plugging in 1.5. There is no meaning to plugging in pi. I cannot plug in pi, I cannot plug in 1.5. I can only plug in whole number values. So my graph is just a bunch of dots. right, any questions about what a sequence is? Okay, let's look at a second example then. Alright, so in this example, an is equal to 1 over n. Alright, so I can start to write out some of my terms here. A1 is going to be 1 over 1, which is 1. A2 will be 1 over 2. A3 is going to be 1 over 3. And I can keep going with this. Remember, this notation up here, A is the name of my sequence, and the N is my input value, kind of like saying A of N. And so I can keep going with this. A4 is going to be 1/4, etc. And so I might write this sequence as, I can either write the formula an equals 1 over n, or I can write my sequence by listing these numbers in order inside curly braces. So 1, comma 1/2, comma 1/3, comma 1/4, comma dot, 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 tells me that that list goes on forever and ever and ever. And we can graph this sequence. Graph an equals 1 over n. So I'll graph for n values 1, 2, 3, and 4. So when n is equal to 1, our output value is a 1. When n equals 2, our output value is a 1/2. When n equals 3, our output value is a 1/3. When n equals 4, our output value is a 1/4. And so my graph looks like those 4 dots. Now, it continues on, and I can kind of imagine in my head that this looks an awful lot like 1 over x. F of x equals 1 over x, except that I don't have all the in-between points. I only have the specific dots that occur by plugging in the whole number of values. Okay, any questions or comments about that one? Okay. So let's look at one final example where I give you the formula for this sequence. And so in this example, we have an is equal to 2 plus -1 to the n over n. All right, so here's what I would like you to do. I would like you to write down values for A1, A2, A3, and A4. One. Okay, so we've got a value of 1. How about for A2?
2.5.
2.5. Okay, how about A3?
1 2/3.
All right, so 1 2/3 also, so 1 plus 2/3, or approximately 1.66. Okay. What A4?
2.4.
2.25. Okay, so we've got a bunch of numbers here, and I purposely approximated on A3 here. So here are some values that we have. Now, I want to point something out here as well. Okay? So these numbers are all pretty nice, but when I look at them, I don't see a lot of pattern that's going on here. So something that I might also do is to see the pattern that's going on. I might actually not simplify these numbers. So I might write A1 as 2 minus 1. And I might write A2 as 2 plus, so I know the plus because I've got -1 squared over 2, so 2 plus 1/2. And A3 as 2, and now I've got negative 1 to the third, so that's a minus over 3, so 2 minus a third. And then A4 is 2 plus 1/4. So some things that I can see here are that this negative 1 on the top, negative 1 to the end, that forces me to have an alternating sign, a minus and then a plus and then a minus and then a plus. And all of these numbers on the right-hand side are being added or subtracted from 2. And so if I go ahead and graph this sequence, 2 plus negative 1 to the end over n, when I'm graphing this sequence, 1, 2, 3, 4, I'm sort of bouncing back and forth across the line y equals 2. And so when n is equal to 1, A1 is 2 minus 1, so I'm 1 unit below the 2. And then for A2, I have 2 plus a half. And so I'm going to go a half above the 2, and then I'm going to go 1/3 below the 2, and then 1/4 above the 2. And so each time my dots seem to be getting closer and closer to this line y equals 2, but they're bouncing back and forth, alternating above and below that y equals 2 line. So this example of a sequence is not a sequence where I can connect the dots necessarily and come up with a function like a nice curve like we're used to seeing, because these dots really are bounce, 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 up and down and up and down and bouncing up and down. I can't just connect those the way that I can over here. I can almost, and you might see me doing this, but you really don't, because I'm not really connecting these dots. I just sort of thinking in my head f of x equals 1 over x. Can't do that with this one over here. Okay, so this is a third example of a sequence. Any questions about that sequence?
No, it's
Time?
yeah.
Okay, awesome. So I want to leave you with the following thought to think about for the beginning of next class. So let's say that we are given the sequence. Let's see, I'm going to start with 3, negative 3, positive 3, negative 3, positive 3, negative 3, positive 3, negative 3, and hopefully you get the pattern by now. And so this is our sequence. And I'm writing this sequence out so that I have my curly braces on the outside. I have three periods at the end, and that says the sequence goes on forever and ever and ever. The first term, A1, is 3. The second term, that's our A2, is negative 3. The third term, A3, is positive 3, and A4 is negative 3. And so the question now becomes, can we write a generic formula for this sequence? So what is a good formula for A subscript n? I know that 1, 2, 3, 4, 5, 6, 7. A7 is equal to positive 3 and A8 is equal to negative 3. How can I write a formula for the nth term in my sequence? So that's something to think about for next time. So in addition to the practice problems,